It began with a curtain of darkness, thicker than any night we know, a wall of gas and dust near the center of our galaxy, a place so dense that even starlight could not escape. Astronomers had known its name for decades, Sagittarius B2, a colossal molecular cloud drifting only a few hundred light-years from the Milky Way's heart. From Earth it looks silent, a black patch that swallows light. But in September 2025, that silence broke. The James Webb Space Telescope turned its golden mirrors toward that shadow and saw what no human eyes ever could. Through the invisible glow of infrared light, the darkness opened. Behind the dust, a city of stars emerged. Bright, new and restless. Thousands of suns, still young, still forming, hidden inside what was once thought to be emptiness. For astronomers, it was like watching a heartbeat through the skin of the galaxy. Each pulse of light told a story of creation happening in real time. Gas collapsing, stars igniting, radiation carving tunnels through dust, the universe building again, right here in our own home. Webb's images looked almost unreal. Ribbons of gold and crimson wrapped around specks of blue. It was not art, it was physics, revealed by the sharpest eyes humanity has ever built. Sagittarius B2 is the largest and most active star-forming region in the Milky Way. It holds enough material to make millions of suns, but it lies hidden behind veils of gas so thick that visible light cannot escape. Only Webb's infrared instruments, NARCam and MIRI, could pierce that veil. When those images arrived, scientists across NASA, ESA, and the Canadian Space Agency stared in silence. They were looking at the most crowded nursery in our galaxy, a place where stars are born faster, brighter, and more violently than anywhere near Earth. The colors were false, but the truth they carried was real. Every pixel of light came from something alive, a new sun pushing through its cradle of gas. Some were massive, glowing hot enough to sculpt the clouds around them. Others were small, just beginning to fuse hydrogen for the first time. In this one region, nearly half of all stars forming near the galactic center are born. It covers only a small slice of space, yet it outshines almost everything near it. Astronomers call it a factory of stars, a furnace of chemistry and gravity working in silence 27,000 light-years away. The first data came not with noise, but with stillness, the kind of stillness that follows awe. One researcher later said, "It was like seeing the Milky Way's heartbeat for the first time." What Webb found inside Sagittarius B2 was more than light. It was movement, structure, and purpose. Filaments of dust curling like smoke, cavities carved by radiation, dark pockets where future suns still slept, each pattern a signature of creation in progress. No other telescope had ever seen it this way. Radio telescopes had mapped its outlines, tracing the molecules that fill it. Infrared satellites had sensed its warmth. But Webb saw through it, layer by layer, like peeling the skin of a living world. It found hidden H2 regions, glowing shells of ionized gas around young massive stars that radio surveys had missed. It found sharp asymmetries, straight boundaries where gas seemed cut away, as if shaped by unseen forces, and it found an unexpected quiet. Despite all the light, there were fewer young stellar objects than models predicted. Perhaps star formation there had only just begun. In that contradiction, a storm of stars that was still a beginning, lay the wonder of the discovery. The images from Webb's NARCam showed one truth. Even inside the most obscured corner of our galaxy, the laws of creation are still at work. Gravity still gathers dust into stars. Radiation still fights for escape. And light, even trapped for millennia, still finds a way to shine. When the first image was released, the public saw colors. Scientists saw history. Every glow was a timestamp, marking the birth of something that would outlive us all. This was not a distant galaxy from the dawn of time. This was home. The Milky Way showing us how it still builds itself from the inside out. For the first time, we were looking not at a distant past, but at a living present. And in that light, Webb reminded us of something simple and eternal. The universe is not finished. To understand the wonder of Sagittarius B2, we have to step back, far back, and see where it lives. The Milky Way is not a quiet place. It is a spiral galaxy with hundreds of billions of stars, stretched into arms that twist around a bright center. From our view on Earth, we sit about 27,000 light-years from that heart. And in that heart lies something restless, a supermassive black hole named Sagittarius, a star. Around it swirls chaos, radiation, magnetic fields, and rivers of gas drawn by gravity. This region is called the galactic center. It is crowded, hot, and heavy. Here, stars are packed thousands of times more tightly than near the Sun. Clouds of hydrogen and carbon monoxide drift like cosmic storms. Among them lies a giant, a cloud so massive it bends radio waves, so dense it hides its own light. That is Sagittarius B2. Astronomers call such structures molecular clouds. They are the raw material of stars, the universe's womb. Inside them, gravity slowly gathers gas and dust until the pressure ignites nuclear fusion. Each newborn star then begins to push back, sending winds that carve tunnels through its birthplace. This battle between collapse and resistance is how galaxies grow their generations of suns. For decades, scientists had mapped Sagittarius B2 using radio telescopes. They traced ammonia, formaldehyde, and even molecules of alcohol drifting in its depths. But no one had ever seen its core. Not truly. The dust was too thick, the extinction too high. Visible and infrared telescopes could not see through it. The Milky Way was keeping one of its greatest secrets close. When the James Webb Space Telescope entered service, that changed. Unlike any instrument before it, Webb could see deep into the infrared, light that slips between dust grains like whispers through smoke. It was built exactly for places like this, dark, hidden nurseries where light is born. To look at Sagittarius B2 is to look into a storm. It spans more than 100 light-years, with filaments that twist and collide like ocean currents. In the center lies a cluster of massive stars so hot they flood their surroundings with ultraviolet radiation. That energy ionizes hydrogen gas, creating bubbles of light called H2 regions. Each bubble marks a cradle where new stars are trying to break free. But the galactic center is no peaceful cradle. Tides from the black hole pull at the cloud's edges. Cosmic rays sweep through it. Supernovae in nearby regions blast shock waves that compress some areas and shred others. In that violence, Sagittarius B2 endures, building stars in defiance of chaos. When Webb focused its golden mirrors on that spot, scientists were not sure what they would see. Some expected only diffuse glow. Others hoped for a few bright knots of formation. What appeared instead was structure, layer upon layer of gas and dust arranged like the folds of a living organism. It revealed two main regions: a low extinction zone, where light escapes more easily, and a high extinction core, where even Webb's powerful instruments struggled to see. The outer layers shone with scattered starlight. The inner ones glowed in hidden heat. This division told a story. The cloud was not static. It was evolving, reshaping itself as gravity and radiation fought for control. Near the edge of the image, a sharp boundary appeared. It looked unnatural, a straight line slicing across swirling gas. Astronomers think it may be the mark of an enormous shock front, where magnetic pressure or an older stellar explosion cut through the cloud. Whatever caused it, the line showed that Sagittarius B2 is not gentle. It is sculpted by forces on a galactic scale. Inside, temperatures range from near absolute zero to thousands of degrees. Some pockets are so dense they block every wavelength of visible light. Others are hollowed by newborn stars whose winds have already cleared paths outward. It is a balance. Collapse and resistance, death and creation playing out together. From this distance, 27,000 light-years away, the entire region looks small on Webb's image sensor. Yet within that patch of sky lie enough materials to forge millions of suns and billions of planets. It is a galaxy within a galaxy, a microcosm of how everything once began. Astronomers studying the data realized something profound. Even in a galaxy as old as ours, Star birth is still fierce at the core. The Milky Way is not fading. It is alive, breathing through regions like Sagittarius B2. And so to look at that image is to see both past and present. Every star there is young, but the process that shapes them is ancient. It is the same physics that lit the first stars of the universe billions of years ago, only now it happens close enough for us to watch in detail. The heart of the Milky Way is still writing its story in light, and Webb, patient and precise, has become its witness. No human eye could ever see inside Sagittarius B2. The dust there blocks almost everything. Even the most powerful ground telescopes see only shadows. But Webb was built to see the invisible. Its mirrors, gold-coated and cold as space itself, were designed to catch the faintest heat from the universe. That heat, stretched across time, becomes infrared light, and infrared light is the language of the hidden. When Webb turned its gaze toward the galactic center, it used two instruments, NIRCam and MIRI. Together they act like twin hearts of sight. NIRCam, the near-infrared camera, sees the shorter wavelengths, sensitive to glowing stars and warm gas. MIRI, the mid-infrared instrument, goes deeper, into the colder dust and molecules that form new suns. Their teamwork is what makes Webb unique. One shows the fire, the other shows the fuel. At the start of the observation, the region looked black. Then, pixel by pixel, light appeared. Each new frame exposed another layer of the hidden city. The process took hours, but what came back looked like something alive. There were rivers of gas curving like veins, cavities that glowed red from trapped radiation, and threads of blue-white light, baby stars bursting through the mist like sparks from a forge. Webb's resolution is so sharp that it can see details smaller than a single light-year across at that distance. That means it can trace where a single cluster of young stars begins to push aside its own cocoon of gas. To the human eye, the final image looks like a painting. Red, orange, gold, and deep black. But those colors represent temperature, density, and chemical makeup. Red is cold dust. Gold is heated gas. Blue and white mark stars that have cleared their surroundings. The combination told astronomers something powerful. Sagittarius B2 is not one smooth cloud. It is layered like a geologic cross-section. Each layer marks a different phase of star birth. In the outer zones, stars are beginning to form, still wrapped in filaments of hydrogen. Deeper in, massive clusters blaze hot enough to ionize their neighbors. And in the very core lies a dark knot, so thick that even Webb can only glimpse its outline. That is where the next generation of stars sleeps, unseen. MIRI's data showed strange arcs cutting through the scene. They are outflow cavities, tunnels carved by stellar winds where light escapes. Radiation from young massive stars has punched holes in the cloud, letting infrared rays leak outward. Even in the densest regions, light finds its way out. One scientist described it as the cloud breathing. Every time a star ignites, it exhales. Its radiation clears a pocket, and the whole structure shifts. Over millions of years, this rhythm builds the architecture of the Milky Way. Webb also revealed a pattern of sharp asymmetry. Along one edge, the gas cuts off in a nearly straight line. It looks like someone sliced the cloud with a blade. Researchers think this boundary marks where outside forces, perhaps a shock wave or magnetic front, compressed the material into form. The image captured that moment of pressure, frozen in time. It shows how violent and fragile star birth can be. The more scientists studied the image, the more puzzles appeared. For all its brightness, the region holds fewer young stellar objects than expected. That suggests the star formation here might be newly triggered, a process just beginning its climb. It could mean that we are witnessing Sagittarius B2 in its awakening phase, moments before it turns into one of the densest star clusters in the galaxy. In cosmic terms, we caught it mid-breath. What Webb recorded is not only a snapshot, it is a promise. As future missions watch this region again, they will see the glow change, the brightness of stars increasing, the shadows moving. Star formation is not still. It is motion, measured in centuries. The telescope's engineers once said Webb was like a time machine. But when it looked into Sagittarius B2, it did not travel to the past. It showed us the present, alive, turbulent, and full of beginnings. It reminded us that the universe is still creating. Even inside its oldest heart, Sagittarius B2 is not supposed to make sense. It is too bright, too massive, too alive for the place it lives in. At the very center of the Milky Way, gravity crushes everything. Radiation from nearby stars burns through clouds. Magnetic storms twist the gas into chaos. Yet somehow, in the middle of that storm, life begins. This is the paradox. A region that should destroy stars instead creates them. A furnace that should evaporate dust instead hides it. To understand why, astronomers compared Webb's data with older maps from radio telescopes and X-ray surveys. The results were stunning. Even though Sagittarius B2 makes up only a small part of the galactic center, it is responsible for nearly half of all the new stars born there. It is a powerhouse operating inside one of the harshest environments in the galaxy. In most galaxies, star formation slows near the core. The gas becomes too hot, too stirred by energy from the central black hole. But our galaxy is different. Somehow its heart still beats. The black hole does not silence creation. It surrounds it. Webb's infrared images revealed that Sagittarius B2 is both chaotic and organized. It looks like an explosion frozen in motion, yet every filament has direction. It is as if unseen hands are shaping it, balancing destruction with design. The paradox deepens with temperature. The outer layers are cold, only a few dozen degrees above absolute zero. The inner regions reach thousands of degrees as newborn stars pour radiation into their surroundings. Between those extremes lies a thin layer, neither hot nor cold, where chemistry thrives. Here, molecules form that will someday seed planets and perhaps life. In the middle of violence, chemistry finds peace. Scientists call this the Goldilocks zone of creation. It is where the pressure is just right for stars to ignite without tearing their cradles apart. Webb's data showed that Sagittarius B2 holds many such zones, stacked one inside another like the rings of a tree. But something about it breaks the rules. In the densest areas, radiation should be trapped completely. Yet MIRI detected narrow paths of escaping light. These are the outflow cavities, tunnels cut by stellar winds that let energy escape. They act like valves, preventing the cloud from collapsing too quickly. Without those vents, the entire structure might implode before stars could stabilize. Instead, the pressure releases slowly, allowing the cycle to continue. Nature built its own escape routes. This delicate balance, pressure and release, darkness and light, is what makes Sagittarius B2 so extraordinary. It is not just forming stars. It is managing the act of creation under impossible conditions. One researcher described it as a living contradiction. He said, "It's both the furnace and the shelter. The paradox extends to its symmetry. Most molecular clouds are lumpy, irregular, shaped by chance. But Sagittarius B2 has sections that look almost geometric. One side shows a clean cutoff, as if sliced straight by cosmic forces. No one knows why. Some think it was struck by an ancient supernova wave. Others believe the Milky Way's magnetic field compressed it into shape. Whatever the reason, it proves that even chaos in the galaxy can leave behind precision. And then there is the silence. For all the brightness, Webb found fewer small stars than expected. Where astronomers expected hundreds of young stellar objects, they found only a handful. The rest may still be forming, invisible inside the deepest dust. It means we are seeing Sagittarius B2 just as it begins to wake. The first sparks are visible, but the real storm has not yet begun. It is like watching dawn arrive over a sleeping city. The lights are turning on one by one, but the streets are still quiet. This timing makes Sagittarius B2 priceless to science. It offers a glimpse of the exact moment when gravity wins, when dust becomes star. It is a bridge between potential and reality. Every paradox within it, heat and cold, order and chaos, birth and collapse, tells us that creation is not clean. It is struggle. It is tension held together by law and chance. And somehow inside that struggle, the galaxy keeps building its future. Webb did not just photograph beauty, it photographed contradiction made visible, a reminder that even in the most violent places, light does not surrender. It adapts, it escapes, it finds a way. In Sagittarius B2, light and shadow are not enemies. They are partners, dancing inside the same storm. And in that dance, the Milky Way remembers how to create. To understand Sagittarius B2, we have to open it layer by layer, like a vast onion made of gas, dust, and gravity. What Webb revealed was not a single object, but an ecosystem. Every fold, every pocket, every whisper of heat had meaning. At the outermost edge, where light from the Milky Way leaks through, lies the cold molecular frontier. Here the temperature hovers near absolute zero. Hydrogen atoms drift lazily, bonding into molecules. Tiny grains of carbon and ice form thin filaments stretched by turbulence. These are the nursery walls, the raw material waiting for collapse. Step inward, and the view changes. The infrared glow begins to pulse. This is the warm transitional zone, where gravity starts to win. Cloud fragments contract, pulling gas toward invisible centers. Webb's NIR cam showed streaks of orange and gold here, each one tracing a current of falling matter. Some of those flows end in silence, others ignite into stars. Deeper still lies the active heart, a labyrinth of radiation and pressure. In this layer, newborn stars fight their way free. They pump ultraviolet light into their surroundings, ionizing hydrogen into glowing shells called H2 regions. These bubbles overlap, merging into one another like ripples on water. Every bubble is a declaration that a new sun has arrived. Yet even inside this chaos, order exists. Webb's data revealed fine filaments only a tenth of a light-year wide. They twist into braids, guiding matter like cosmic threads feeding a loom. Magnetic fields run along them, shaping the cloud's skeleton. It is architecture written in magnetism and motion. At the center rests the core of extinction, so dense that not even Webb can see through it completely. Here the light dies, swallowed by dust 1,000 times thicker than any smoke on Earth. And somewhere inside that darkness, the next generation of massive stars is forming. Their light has not yet broken through, but their gravity is already sculpting everything around them. This inner region is alive with chemistry. Molecules of ammonia, methanol, and formaldehyde swirl in concentration. They are the same building blocks that once seeded the early Earth. Astronomers know this because Sagittarius B2's radio signature shows the same spectral fingerprints as prebiotic molecules. Life's precursors are being stirred even in the heart of a stellar furnace. Another strange feature stood out: the outflow cavities. Webb's MIRI instrument caught them as narrow blue tunnels cutting through red dust. They are escape routes carved by radiation pressure. Without them, the stars would smother in their own heat. Through them, light escapes, and so does knowledge. Each cavity acts as a cosmic lighthouse, sending infrared beams through the fog. Those beams carry the story of temperature, density, and movement. By reading them, scientists can reconstruct the anatomy of the cloud in 3 dimensions. One cavity is especially striking. It stretches almost 5 light-years across, ending in a sharp line of emission. It may have been blasted open by a cluster of massive stars whose winds joined into a single surge. That surge likely created the straight edge we see at the cloud's border, a scar left by creation itself. Webb's instruments also detected faint halos beyond the main body of the cloud. These halos contain scattered dust and low-density gas pushed outward by past starbursts. They are the remains of older generations, proving that Sagittarius B2 has been building and rebuilding for millions of years. Everything inside the image fits together like organs in a living body. Cold outer layers feed the warm middle. The middle fuels the hot heart. The heart breathes through its cavities, releasing energy that stabilizes the whole. It is self-regulating, self-balancing, almost self-aware in its persistence. And this is why scientists call it a molecular complex rather than a single cloud. It behaves like an organism, not an object, a structure that consumes, transforms, and produces. a system designed by the laws of physics to create light. To see it through Webb is to witness anatomy at a galactic scale. There is no empty space, only layers of purpose. Every dark vein hides motion. Every bright spot hides pressure. And together they form the most productive nursery in the Milky Way. From its cold shell to its blazing center, Sagittarius B2 is a portrait of how the universe builds beauty from turbulence. Its body is made of gravity and dust, but its heartbeat is creation itself. Every discovery must face doubt before it becomes truth. And Sagittarius B2 was no exception. When Webb's first data arrived, scientists did not celebrate right away. They questioned everything. Could the brilliant lights in the image be artifacts? Could the apparent tunnels be tricks of dust or temperature? Astronomy, after all, is built on verification. For decades, radio telescopes had already studied Sagittarius B2. They traced molecules, ammonia, carbon monoxide, methanol, each one marking temperature and density. From those signals, researchers built models of what the interior might look like. But Webb's infrared vision went beyond radio. It reached into the physical structure itself. Now scientists could see the shapes their data had only hinted at. The confirmation came slowly, line by line, through spectral analysis. Webb's NIRCam and MIRI instruments measured light across hundreds of wavelengths. Each wavelength told a different story: heat, dust, chemistry, motion. When the patterns matched known molecular fingerprints, confidence grew. Ammonia absorption lines matched predictions from ground-based observatories in Chile. Methanol emission peaks lined up perfectly with older radio maps from ALMA and APEX. But then Webb added something new: faint features no one had ever seen before. Subtle signatures suggesting complex organic molecules, long carbon chains that could be precursors to amino acids. It was a quiet but profound moment. Even in a furnace of radiation, chemistry was thriving. Life's ingredients were assembling in the shadows of newborn stars. The validation went further. In earlier studies, astronomers suspected that Sagittarius B2 hid clusters of H2 regions, hot zones of ionized hydrogen surrounding young, massive stars. Radio waves hinted at them, but never clearly. Webb resolved them one by one. Dozens of tiny glowing spheres, each about a light-year wide, nested inside the dust. They were the fingerprints of creation, stars caught in the act of igniting. Even more surprising, Webb revealed new H2 regions that no radio telescope had detected. These were likely shielded from radio signals by thick dust, but visible in the mid-infrared. It proved that the old maps were incomplete. The sky had been hiding more stars than we knew. Another puzzle was the cloud symmetry. Earlier instruments saw a broad, uneven structure. But Webb showed sharp boundaries and straight edges, signs of external forces shaping it. The discovery of a near-linear gas wall confirmed that the cloud had been hit by a shockwave or compressed by magnetic fields. It wasn't just forming stars, it was reacting to its galactic environment. As the data poured in, computers across the world began to process terabytes of information. Teams in the United States, Europe, and Japan compared Webb's observations with older catalogs. Every test confirmed the same truth: the image was real. The light patterns were consistent, the chemistry authentic. What Webb saw was not illusion, it was revelation. This validation process matters because the galactic center is one of the hardest places to study. Radiation from the supermassive black hole Sagittarius. A star floods the area with noise. Cosmic dust distorts light like fog distorts a lantern. For Webb to separate truth from distortion, it needed precision beyond anything before it. And it delivered. Infrared calibration showed that the signals from Sagittarius B2 were not contaminated by background sources. Every photon could be traced to its origin within the cloud. That level of clarity was unheard of. It turned data into anatomy. The discovery phase began once the doubts were silenced. Scientists mapped the temperature gradients inside the cloud and found something unexpected. Heat was escaping through narrow corridors, not evenly. That meant energy from young stars was leaking in organized patterns, carving pathways like arteries in a living body. These outflow corridors matched the cavities seen in the images. They confirmed that light had indeed found exits in the densest regions. It was proof that the cloud could self-regulate, releasing pressure to avoid collapse. The MIRI instrument detected infrared glow from polycyclic aromatic hydrocarbons, or PAHs. These molecules form when carbon atoms bond into rings, usually in places exposed to strong starlight. Their presence meant that massive stars were already influencing their surroundings, shaping chemistry even before they fully matured. Another discovery came from Webb's precise distance measurements. Using parallax data, astronomers calculated that Sagittarius B2 sits roughly 27,000 light-years from Earth and about 330 light-years from the galactic center. That small offset means it sits close enough to feel the gravity of a Sagittarius A star, but far enough to survive it. It lives on the edge of danger, close to the galaxy's heart, but not consumed by it. One researcher compared it to a city built beside a volcano. Destruction and creation living side by side. Even the motion of the gas defied expectation. Spectroscopic readings revealed that different parts of the cloud were moving at wildly different speeds, some approaching, some receding. It meant the entire structure was rotating, tumbling, perhaps colliding with smaller clouds nearby. Every collision fed it with new material, keeping star formation alive. When all the data were assembled, one conclusion became clear. Sagittarius B2 is not a static object. It is an evolving system, constantly fed, constantly remade. It is as dynamic as the stars it births. In those findings, Webb confirmed what astronomers had long suspected, that the Milky Way's core is still growing. But it also delivered something no one expected, a glimpse of star formation under extreme conditions that mirror the early universe. The same physics that built the first galaxies is at work again, right here in our backyard. With that realization, the mission changed. Sagittarius B2 was no longer just a map to study. It became a time capsule, a living record of how creation persists even in the shadow of destruction. And for the scientists who saw those glowing threads of light for the first time, it felt like standing at the edge of understanding and peering one step further. When Sagittarius B2 finally surrendered its secrets, the real questions began. How could a single cloud near the Milky Way's core create so many stars under such impossible conditions? And what did it mean for everything we thought we knew about how galaxies build themselves? Astronomers began testing every theory. Some blamed gravity, others blamed timing. A few suggested that Sagittarius B2 might be living proof that the rules of star formation are not universal. The first idea came from those who study galactic tides. They argued that the enormous gravitational pull of Sagittarius A star, the black hole at the center of our galaxy, might actually help the process instead of hindering it. As the cloud orbits through the dense core, gravity compresses it again and again, like a heartbeat made of gas. Each pass squeezes the molecules tighter until collapse becomes inevitable. If this is true, Sagittarius B2 is both victim and survivor of the black hole's influence. The same force that could tear it apart is the one that drives it to create stars. Another theory focused on magnetism. The Milky Way's core is threaded with powerful magnetic fields. Webb's data hinted that these invisible lines might guide gas flows inside Sagittarius B2, giving it its strange, organized shape. Magnetic pressure could also explain the sharp edges that looked like they were cut by a cosmic knife. If those fields are strong enough, they could sculpt the gas into narrow channels where gravity and radiation can coexist, keeping the cloud alive longer than models predict. Then came the collision theory. Spectral readings showed that parts of Sagittarius B2 were moving at very different speeds. Some scientists believe two smaller clouds may have collided millions of years ago, merging their material into one massive structure. That collision could have sparked a wave of star formation still unfolding today. In that view, Sagittarius B2 is not ancient. It is a newborn, forged by impact and rebirth. Yet the biggest tension came from numbers. Star formation in the Milky Way is usually slow and inefficient. Most molecular clouds waste almost all their gas before stars form. But Sagittarius B2 seems different. It is turning its material into stars at a rate that breaks expectations. If this efficiency is real, then our models of how galaxies evolve may need rewriting. The equations that describe how matter becomes light might be missing a vital term. Some researchers saw something deeper. They noticed that the conditions inside Sagittarius B2, high density, intense radiation, rapid collapse, mirror those in the early universe, when the first galaxies were born. In a way, the Milky Way's core is replaying its own origin story. Studying this cloud could reveal how the first massive clusters formed billions of years ago. It is like having a time machine inside our own galaxy. Webb's detection of complex organic molecules raised another mystery. How can fragile chains of carbon survive in such a violent environment? Normally, radiation destroys them in seconds. Yet in Sagittarius B2, they seem protected by the dense dust. This could mean that the seeds of life, simple organic molecules, can endure even near the heart of chaos. If so, then the universe is more generous than we imagined. Life's chemistry might begin anywhere there is dust and time. But one question remains the loudest. Where are all the small stars? In most stellar nurseries, low-mass stars vastly outnumber the giants. But Webb found the opposite. Massive stars dominate the picture. Either the small ones are still invisible, or the rules are different here. If Sagittarius B2 produces mostly giants, that would change the balance of energy in the Milky Way's center and reshape our understanding of galactic feedback. It could also explain why the region shines so brightly in infrared and radio light. Big stars live fast and die young, scattering heavy elements back into the cloud. That process might be fueling the next generation, even before the first has finished burning. Inside every scientific debate lies a human one. Some astronomers saw in Sagittarius B2 a sign that the universe is more chaotic than ordered. Others saw precision hidden in the chaos. But all agreed on one thing. Webb had forced them to look again. Every theory built over decades now had to face the light of new evidence. The data do not resolve the paradox. They sharpen it. Star formation is not a single process but a spectrum of possibilities. And in that realization lies the beauty of science. Discovery is never an ending. It is a deeper beginning. The tensions remain, but they are creative ones. Every unanswered question becomes an invitation to study harder, to build better models, to see further. In that sense, Sagittarius B2 has already fulfilled its purpose. It has reminded humanity that the cosmos is still full of surprises, and that even at the edge of knowledge, wonder continues to lead the way. Once the data had been confirmed and theories had begun to take shape, scientists turned to the question that always follows discovery. What does it mean? Webb's view of Sagittarius B2 did more than reveal a single star-forming region. It forced astronomers to rethink how entire galaxies evolve. In the past, researchers looked far away, to the edge of the observable universe, to understand the beginning of everything. Now they realized that a version of that beginning was still unfolding inside our own galaxy. Sagittarius B2 is not a fossil of ancient creation. It is a living sample of it. By studying it, scientists can test their simulations of early galaxies against something close enough to touch with light. Every temperature map, every chemical spectrum, becomes a window into the way the first stars once formed inside the young cosmos. The discovery also reshapes how we see the Milky Way itself. For decades, we imagined our galaxy as a mature, settled system, a grand spiral long past its youth. But Webb showed otherwise. The Milky Way is still growing from the inside out. Its heart is still capable of building new suns, new planets, and perhaps new stories of life. Sagittarius B2 is proof that evolution never stops. It shows that even in old age, galaxies can still create. Another implication lies in energy balance. Massive stars pour out radiation, winds, and eventually supernova blasts. That energy feeds back into the cloud, sometimes destroying it, sometimes reshaping it into new forms. This feedback loop is one of the central engines of cosmic evolution. Webb's images revealed it in motion, light escaping through tunnels, gas collapsing elsewhere to begin again. Understanding this cycle is key to predicting how galaxies breathe across billions of years. Then there is chemistry. Sagittarius B2 is a chemical laboratory on a scale no human can reproduce. Inside it, molecules form, break, and reform under extreme conditions. By mapping these reactions, scientists can trace the steps that turn simple hydrogen into the complex carbon molecules that one day become biology. The presence of organic molecules in such a violent place expands the definition of where life's building blocks can survive. It hints that the universe may be full of invisible beginnings, chemical seeds scattered everywhere, waiting for calm skies. Perhaps the greatest implication is psychological as much as scientific. Before Webb, astronomers thought that star formation required peace. Cold, quiet clouds far from galactic centers. Sagittarius B2 shattered that idea. Here stars are born inside turbulence and fire. They grow in the glare of radiation, surrounded by gravity strong enough to crush them. And yet they survive. They shine. It is resilience written in light. If stars can form here, they can form almost anywhere. It means that galaxies may be far more efficient at creating stars than we once believed. The story of cosmic growth is not gentle. It is determined. For the scientists watching those golden images unfold, the implications reached beyond physics. Sagittarius B2 became a metaphor for human curiosity. Like the cloud itself, our species forms meaning out of darkness. We look through noise, through doubt, and find patterns that make us feel part of something vast. The Webb telescope is more than metal and mirrors. It is an extension of the human will to see. Each photon captured by its detectors began its journey long before humanity existed, crossing thousands of generations to arrive in our instruments. In that sense, every discovery is an act of inheritance. We are catching light meant for us before we were born. The implications of Sagittarius B2 stretch forward too. Future telescopes, like the next generation of radio arrays and X-ray observatories, will build on Webb's findings. They will map the magnetic fields, measure turbulence, and follow the life cycle of these stars as they grow and die. In 10 or 20 years, scientists may have complete 3D movies of this cloud evolving. We will watch suns ignite and clouds disperse, seeing creation unfold not as theory but as sequence. Each frame will remind us that the cosmos is not frozen in the past. It is happening right now. When the Webb telescope first turned its golden eyes toward the Milky Way's heart, it did more than gather light. It gathered proof that creation never sleeps, not even in the oldest corners of the universe. For centuries, humans have looked up at the night sky and imagined endings: the death of stars, the silence after collapse, the final ember of a cosmic age. But Sagittarius B2 tells a different story. It shows that even in chaos, life finds rhythm. Even in destruction, there is renewal. In the center of that cloud, stars are still being born from dust older than Earth itself. Their light cuts through darkness that once seemed eternal. Each spark, each flare is a statement that the universe is not fading, it is breathing. When astronomers measured the heat and movement inside Sagittarius B2, they realized something profound. The same patterns appear everywhere, in tiny nebulae, in distant galaxies, even in the frozen corners of interstellar space. It is a universal heartbeat, repeating across scales too vast to comprehend. The cosmos builds, burns, and rebuilds. That rhythm is older than time and younger than light. Webb's mirrors did not just record data. They captured a moment of truth, that the laws of physics and the laws of empathy might not be so different. Both depend on connection. Matter binds through gravity. Humans bind through meaning. In both, the invisible holds everything together. When the first images of Sagittarius B2 appeared, gold and amber threads glowing through blackness, scientists described them as beautiful. That word, though unscientific, was the most accurate. Because beauty is what happens when understanding meets wonder. It is when data becomes story. Standing beneath the night sky, we are small, but not separate. The elements in our blood, the oxygen in our lungs, the carbon in our cells, All were once born in clouds like Sagittarius B2. The same forces that shaped those stars shaped us. We are quite literally the dust of that same creation cycle. To look at Webb's image is to look into ancestry, not of families or nations but of atoms. It reminds us that our beginnings are cosmic, and our endings, too, will one day feed new light. In ancient times, humans worshipped stars because they could not explain them. Today, we measure them, but the awe remains. Webb has given us a new vocabulary for that awe: wavelengths, spectra, formation zones, molecular clouds. Yet beneath the technical words, the same feeling endures: the quiet recognition that we are witnessing the act of becoming. When light travels across 27,000 light-years to reach our instruments, it carries memory. It carries the moment when atoms first fused, when pressure became fire, when nothing became something. And when it arrives, we translate it back into color, shape, and story. We are the universe remembering itself. Sagittarius B2 also whispers a warning. Creation and destruction are twins. Every star that forms will one day die. The same gravity that binds them will eventually tear them apart. But even that death is not waste. It feeds the next generation of light. There is no loss in the cosmos, only transformation. If we listen carefully, the message is not just scientific, it is moral. The universe survives by recycling its own ruin. Perhaps humanity must learn the same lesson, to turn collapse into renewal, to see change not as ending, but as continuation. When Webb finished its observations, the raw data was transmitted to Earth. Strings of numbers, pulses of code. Technicians assembled them, cleaned them, colored them. Then, for the first time, a human eye saw it. The largest star-forming cloud in the Milky Way, alive with light and shadow. Somewhere, a scientist whispered, "We're looking at the universe making stars." But what they were really saying was, "We're looking at the universe making itself." That moment, quiet, almost reverent, marked something rare. A union between reason and wonder, between knowledge and humility, between the seen and the infinite. And so, as Webb continues to stare into the heart of our galaxy, it teaches us what all great discoveries do. That curiosity is our species' brightest flame, and that the act of looking itself is a form of creation. Because every time we lift our gaze toward the stars, we participate in the same eternal process the stars began, turning darkness into light.